Okay, so what we're going to do today is I'm going to finish talking about thermodynamics, and then I'm going to jump into quantum, the next chapter. And part of that's because I want to have a set aside a class day before the next test to study, so that way you can get dedicate another class period to study for the test.
That's next week, right?
Yeah.
Oh.
Oh wait, but then there's not next week. It's the week after.
Sure. Yeah, I didn't realize it was.
I thought it was next week.
I sent an improper email out. It's
How
the
dare you.
9th, right? Let me look at this.
Shame on you.
The
Wait, the 9th
13th.
Oh, okay.
13th.
Okay, good. I was like, the 9th is a Saturday.
Because then, because the 11th is also a holiday. So there'll be problem session on Wednesday after this class as well. So nothing today though.
Problem sessions are only on Wednesdays.
Yeah.
I think that Monday he gets so tired of your shit. He doesn't want to see that much.
Me specifically.
Yeah, not me.
That's not entirely true. Does anybody have any questions about anything before we start? Okay, so jump. Oh, and Friday's last day to take the retest at the testing center, and I'll get that graded by Friday sometime. So that way you'll have the data. It should only take me an hour or two to grade, but I'm gonna wait till everyone's done now. So, okay, so next we're gonna talk about our standard states. And the so what in this, enthalpy and a lot of things are path independent. So path independent also means state function, also means exact differential, also sometimes referred to as a mother function. These all mean the same thing mathematically. So things like enthalpy H are path independent. Is this hard to see? It seems like a little brighter.
Yeah, it is.
Okay, I hear you. It's easier in my eyes, easier in your guys' eyes too.
Yeah, enough.
It's really easy to see right here. But okay, so things are path independent, and because of that, it's kind of like having the smart kids do all the homework and you copy from it. Someone went and calculated out a bunch of things using standard states, and then we can relate them to those standard states. And what's been interesting also is that since the end of the Cold War, the United States and Russia have been collaborating scientifically. And we both did standard states. And in my opinion, the Russian standard states make more sense. For among other things, they use a pressure of 1 bar. 1 bar is 100 kilopascals. We in the United States use an atmosphere, which is 101.3. It's the average pressure of the atmosphere. The Russian one is more engineered. So what did we do? Did we take the one that made more sense? No, we flexed our American muscle, said, Russia, you're taking our standard states, because America. And now Russia uses our standard states. So, and these are the standard states. For a gas, it's the pure gas at a pressure of 1 atmosphere, usually at 25 degrees Celsius. Also as well, for a liquid or solid, is the most stable form at a pressure of 1 atmosphere at a temperature usually 25 degrees Celsius. So what I mean by most stable, if you look at like carbon, for instance, carbon can be graphite, it can be diamond, it can be a nanotube, which is essentially graphite. It can be what called fullerene, C60, C70. So which one do we pick? Graphite. It's also the most common one. So the most stable and the most common. Graphite is what we pick. And for solutions, 1 molar. Then the standard enthalpy change, and notice that there's a degree sign here. That means it's at standard state, and it's when all the reactants and products are in their standard states. And the degree sign indicates standard states. And then the standard enthalpy of formation for a compound, it's the formation of from their elements in their standard states. And a definition for a pure element in a standard state, the heat of formation is 0. So what does this mean? It means that enthalpy H is a relative scale. So we pick a relative amount for the enthalpy, and what we pick for 0 is the elements in their standard states. So, and what does that mean? Well, if you look at certain variables, temperature can be relative and it can be absolute. So Celsius is a relative temperature. 0 Celsius is a freezing point of water at 1 atmosphere. And Kelvin is an absolute temperature. You can't get any slower than not moving. So 0 Kelvin is the cold limit. Now, that means for enthalpy, there is no such thing as absolute enthalpy. So we just pick it all. It's always relative. There are some things that are absolute. Entropy, which we'll learn about next semester, is relative. It's not relative. I'm sorry, it's absolute. Excuse me. Okay, and the standard enthalpy is also referred to as a standard heat. And here is a table of standard enthalpies, and you never have to memorize any of these except for the elements are 0. And I remember in a test question I list this and I don't list the elements, and then I get a lot of students asking me, what's the enthalpy of formation of this element? And I'll tell people it's 0. So even then, if you forget, I'll still tell you. But, and this is an abbreviated chart. A bigger chart, I guess you don't have textbooks per se. If you look into appendix in the back of your book and your ebook, in this book, it is appendix 2 in your textbook. Okay, so there's more in your appendix 2. There's also several books that have this stuff. So the Handbook of Chemistry and Physics has it, and Perry's Chemical Engineering Handbook also has some of these. So there's a much more complete list there, and there's even, I'm sure there's even more complete lists online. So sometimes you have to go to a library and find things in weird, like if you have a really weird compound, you have to look up. I remember one time I had to go to the library to look up a compound. It was barium stearate, I remember. I couldn't find it anywhere, so I did find it at a university library a long time ago. But anyways, so here are the standard states, and let me talk about a formula. So the standard state heat of reaction is equal to the sum of the moles of products, heat of formation of products, minus the sum of the moles of reactants, heat of formation of reactants. And this capital sigma, this means an arithmetic series. So if you have like sigma n equals 1 to 5, 1 over the variable, 1 over n, you just put 1 over 1 plus 1 over 2 plus 1 over 3, 4, 5. So this is an arithmetic series, and sometimes called a Raman sum as well. This is a geometric series, so this is capital pi. These are Greek letters. So this is capital sigma, this is capital pi. Lower pi is like the 3.14159,256, that number. This is capital pi. It means geometric series. It means you multiply things. This sigma means you sum them. It's an arithmetic series. And what is the heat of formation? So I mentioned there the heat of formation. Where is it? The standard enthalpy of formation, right here. The change in enthalpy when a mole of its forms constituent elements to their standard states. So let's look at some of them. Here is the formation of sodium chloride. This is Theodore Gray. He is completely insane. But you can see here, this is chlorine. He's got sodium metal there, and he's shooting chlorine gas into sodium metal, and those are so sodium metal is an element. Chlorine is an element, and he's making salt. That's salt, and now he's salting some eggs, which he intends to eat. And he is, like I said, completely insane. Again.
That knows how to party.
He what?
Sounds like his parties get wild.
He likes to throw sodium parties.
That sounds fun. Can we do that?
I don't think we have any sodium. I don't know where we'd throw it. He likes to he has this big lake. I can show you another video. He has this big lake that he throws sodium into, and it causes an explosion. So he is like the mad scientist. Here's the sodium. There's his lake, and he like has a lever, and then it causes a big boom. There we go. So yeah, he likes to blow things up in his backyard. If you ever want to get this is a cool ebook. I mean, it's pretty expensive. It's like $13 or $14. It depends on your definition of expensive. But that's a fun book. But I know, I'm a chemistry nerd. Of course I'm going to like that. So do you understand what a standard heat of formation was? That what you just saw was sodium chloride. And here is sodium chloride. And you can see it's negative 411.2. And you can see it was exothermic, right? It was giving off energy. And the way that you would determine this is you would take sodium metal plus chlorine gas and react it at 25 degrees Celsius and the pressure of 1 atmosphere, and then see how much energy was evolved. And from that, we know that when you form sodium chloride from sodium metal and chlorine gas, it gives off 411.2 kilojoules of energy per mole. So, you guys understand that? I guess you guys are lucky because you get I get all the questions from the first section, and not that I haven't been teaching this for a long time, but it's fresh in my mind. You're not giving me much feedback. Does that make sense, or is that, okay, it is making sense. Okay. All right, so let's apply this formula.
Okay.
So what is the standard and what is the heat of reaction for this reaction? 4 ammonias plus 5 oxygens makes 4 NOs plus 6 waters. And the formula is the delta H is the sum of the number of moles of products, heat of formation of products, minus the moles of reactants, heat of formation of reactants. These are products. They go first, and then you minus these. So let me do that. So that means your delta H0 reaction, this equals 4 heat of formation of NO plus 6 heat of formation of water, and make sure it's gas, minus 4 heat of formation ammonia plus 5 heat of formation oxygen. Does this make sense? 4, 4, NO, NO, 6, 6, water, water, vapor for gas, minus reactants, 4, 4, ammonia, ammonia, 5, oxygen, 5, oxygen.
Okay.
Make sense? Okay. Which one of these is 0? There's one of them that's 0. Which one's an element?
The oxygen.
Yeah. This one's 0.
Okay.
So then we have to look at the chart. So 4 NOs. So nitrogen, here is NOs here. So it's 91.3. 4, 91.3 plus 6. And make sure that it's water vapor because there's 2 of them. Right, so make sure you put the proper state. So minus 241.8, because if you use the 285.8, that's the wrong number, give you the wrong values. So 2 minus 241.8 minus 241.8 minus the quantity 4, and what's ammonia?
Minus 45.9.
All right. And plus 5 times 0, which makes no sense. False is 0. You put those all in, this is minus 902 kilojoules per mole.
Can you scroll down a bit so I can see the original equation?
Okay. So this is the equation. Heat of reaction is a sum of moles of products, heat of formation of products, minus moles of reactants, heat of formation of reactants. So the products are on the right. They go first. 4, because there's a 4 here. Heat of formation nitrogen monoxide. 6, heat of formation of water, vapor. Minus 4, heat of formation of ammonia. Plus 5, heat of formation of oxygen. It's an element. It's 0. And then we plug in the numbers from the chart and get minus 902 kilojoules per mole. So questions with this?
No.
Yeah. Okay, so it's pretty straightforward. And what's really cool about this, I mean, I feel like a scientist. It's so amazing. But what's really nice about this, you don't have to do the experiments. I mean, if you want to figure out something, you do not. You don't even have to do the experiment. You can just look stuff in a book, and if you have a bit of skill with this, you can calculate the energy of basically any reaction that you want. And why is that important? Well, then that tells you how much energy is given or taken off from a reaction. Also, we'll find out later on that these energies affect the equilibrium. And then because of that, you know where the reaction is going, and you know what the concentration of the reaction will be at the end. And all of this without ever having to go anywhere but your chemistry textbook, your notes, and some paper, pencil, and a calculator. And the internet, probably look this stuff up. Right, so, and that is extremely useful. Extremely, extremely useful. You can predict many, many things. So thermo is very powerful. It's very useful, unfortunately, because I don't like it, but it is very useful. Okay, so let's see if you follow. This is the thermite reaction.
Okay.
I'm in the mood to watch videos. Let's look at the thermite reaction.
Isn't that a balance? Thermite?
It is. Oftentimes a tank buster.
Yeah.
There is aluminum, and then iron. It was mixed with iron oxide, and I've seen this before. It's really hot. It's a lot of heat, and that's a sparkler to provide activation energy. And then there's the reaction, and it generates. Well, it's liquid iron, but we're saying solid. There's liquid iron there in the bottom.
What class do we get to start blowing stuff up?
Not here. Maybe organic chemistry. I don't know if Dr. Fisher does any of the real dangerous labs.
Tippett says he's the Breaking Bad guy.
Yeah, I'm not scientist.
He is a really good synthetic chemist.
Does that mean he's secretly a drug dealer?
I think he's fairly religious. I don't know him personally all that well.
Yeah.
He's got an art supply store.
Huh. Where he launders his money?
I was talking about.
Say the car wash.
It's not. If he does, he's hiding his wealth well.
This is how that teacher almost got fired from Mean Girls.
Yeah.
But the thing is whenever a chemist makes drugs, they always catch him or her. So and the reason why, they do too good of a job. So like whenever the police find drugs in the street that are made by a chemist, they're like, oh, this is someone who knows what he or she is doing. So then they just look at all the chemists. They usually catch the person should say, I was told it was almost always. So, which makes me wonder about the state of street drugs. Okay, so here's the reaction, the thermite reaction. Actually, the thermite reaction is usually liquid iron, but we're making it solid iron because that's zero, because it's an element. So here is the formula. Here is the reaction. 2 aluminums plus iron oxide, iron 3 oxide makes aluminum oxide and 2 irons. And some of the questions from the previous class, this Fe2O3 is one thing. It's not O3. It's not Fe2 and it's not O3. It's not Fe2 and iron is 0 and O3 is ozone. No, it's Fe2O3, heat of formation is right there. And then you have aluminum oxide there, also known as sapphire. And the aluminum and iron are both elements, so they have the relative heat of formation of 0. Has anyone heard of the Hindenburg before? It's a Zeppelin that exploded. And they had iron oxide paint on it and aluminum around it as well. And the combination of the two with a spark from static electricity caused it to explode. And then it had hydrogen in it. So the thermite reaction started happening, and it caught on fire, and then the hydrogen in it exploded, and it killed a bunch of people. There were a lot of people that survived it as well, though, and they were the ones actually that didn't jump. Scary enough. They got burned, but they didn't die.
I got it.
So,
Oh, I got answers.
I just want to try it.
anybody stuck?
He has it.
Raise your
Up
hand.
there, the two,
So any element by itself is 0?
yes.
In its standard states.
Any element.
And it's
And
standard.
it's
state.
diamond is an element, it's carbon, but it's not the standard state. Graphite is the standard state for diamond.
So then,
Graphite is also carbon.
Yes, but we pick, so carbon has a couple forms.
Yeah.
So, I mean, it essentially it's 4 is the most so there's graphite, diamond, C60, C70, but there's also nanotubes. The nanotubes are a lot like graphite, but they're various sizes. They're slightly different. This is, that's not, this is a new edition. There's also graphene, which is a single layer of graphite. So, anyways, there's a couple different forms. So we pick the center state, which is, we pick it. We pick the easiest one, which is graphite. Also, sorry, I'm gonna jump up. Oxygen, for instance, you have O2 and O3. O3 is ozone. We pick O2 as the standard state. Okay, so
the standard state is when it's most stable. For
Typically,
liquid or
yeah.
solid.
this is going to be the products. So what's the product? Al2O3. Minus unit formation of Fe2O3.
No.
So do you get this? That's a product. Product. That's a reactant. Reactant. There's one of them.
Oh,
No two. And then you minus a minus, so it's about 800, negative 800-ish.
Negative 851.5.
There you go. Questions with this?
This is this section.
Huh?
I like this section.
Yeah, most students do. It took me 6 minutes less time to get here than the morning class. So you have 6 extra minutes for me to talk.
Or not. Whatever you fancy. I fancy
Yeah,
it.
academia is the only class or industry, it seems, that people prefer less. Like a 50% off the learning, please. Okay, so we're in a new chapter now, and we're in quantum mechanics. Has anyone ever heard of Schrodinger's cat before? Yeah.
Get it?
What's that?
No.
Yeah. So Schrodinger, who's Schrodinger? I personally really like Schrodinger. I have never met him. He's been dead for decades. But I did go to the Nobel Museum in Sweden, in Stockholm, Sweden, and they had like all the Nobel Prize winners. They give like a short lecture and they record it. And just hearing him talk, he has like the most electrifying voice. He was also, in general, he was a really good person. He also was married and had a mistress, so I guess he was good at other things as well.
Huh.
But I mean, some scientists lead lives that would make the artists blush. So, well, right next to this is Heisenberg's uncertainty principle. It's nothing to do with Schrodinger's equation, but Heisenberg, he was a prick. He was a Nazi jerk. So I'll be try and keep the language to PG. I wouldn't want to meet him, but I would like to punch him in the face. You know. So, but anyways, so not all scientists are amazing people either. But Schrodinger. So at the time, we were trying to figure out the energy levels for the hydrogen atom, which we will do not today, but a subsequent class, and. By legend, Schrodinger went to the conference and he left for a weekend with his mistress and thought about it and came up with his wave equation, which we'll also learn later. And Schrodinger was challenged by this in a way because we'll talk about this later on about the wave-particle duality of electrons, which means electrons, if you look at them and you expect them to behave like a particle, they'll behave like a particle. But if you expect them to act like a wave, they'll act like a wave. So his question was, well, what's an electron when we're not looking at it? What's it like? He said, it's like if I have a box, in the box is a cat, and in the box I have a machine that when I want to open the box, the machine will release gas and kill the cat, or it won't, depending on whether I open the box. And it's like a 50-50 chance, and I can open a box and like, oh, hi kitty. Oh, hi, kitty. Like, oh, dead cat. Oh, kitty, kind of thing.
What?
Yeah. So the idea was, what's the cat like in the box when I don't open it? It's like this half-living dead. It's like the undead kitty that's in here, in this box.
Both dead and not dead.
Yes. That's why you have a dead kitty and a live kitty,
Ah,
right? So that's Schrodinger's cat.
dark.
Yeah, and what Schrodinger was describing, this is something called a superposition. So we haven't learned this yet, but electrons can have spin up, spin down. Their magnetic fields can align spin up or spin down. One's positive, one negative, relative to each other. And but electrons, if you have a single electron, it can be spin up, it can be spin down, or it can be both. And that's called a superposition. And so what? Why do we care? Because we're starting to do quantum computing. Right now, our computers are based off of binary logic, and they're based off of the band gap of silicon. So silicon with no potential in front of it does not conduct electricity. Silicon with 5 volts or greater behind it does conduct electricity. And when silicon conducts electricity, we call that a 1. And when silicon does not conduct electricity, that's a 0. That is our basis for binary for all of our computer programs. We're looking at using electrons as for qubits. And the thing with a qubit, it can be spin up, it can be spin down, or it can be both. And that's not a big deal for one electron. If you have 2 electrons, if you have spin ups, they can both spin up, One can be spin up, one spin down, and that's the same thing as this. And they can both be spin down. But then you can have one that's spin down and have a superposition, or you can have two superpositions, and so on. So now you have more possibilities,
So,
and that messes up the logic.
so binary space 2, quantum space.
The other thing with a quantum computer is that the electrons behave like waves, and then they make interference patterns. So because of that, I mean, if you have like 5, you can figure it out. But if you have 1,000,000 transistors, I mean, if you have a third of them that are superposition, how are you going to decipher that? And, I mean, you can get it to compute something, and it usually actually works faster. But where it really has the application is in passwords. So because passwords are protected by mathematics, and if you have a quantum computer, you could break into a bank in a matter of minutes and a day or two to code nuclear missiles. So it's a simple like a computer with like 100 megahertz kind of thing. So that's what the U.S. government doesn't talk much about quantum computing. Academia does that. So I'm not an expert, but I have friends that were experts.
I just saw something where Google recently put together a quantum computer.
Yeah. Quantum computers, when you tie them to regular computers, are very effective as well, because regular computers are great at just punching out calculations, and quantum computers are better at kind of figuring stuff out. And we are hypothesizing that consciousness may have something to do with quantum computing, but we're not entirely sure. So, I mean, we're still learning, and we don't know where the quantum computer would be in our brain, meaning we don't know what ion or electron would do it. We don't. I mean, there's probably an electron somewhere. The other thing with the human brain, though, it's not just a computer. We have other things like emotions and neurotransmitters, so it's even more complicated than just a simple quantum computer, which makes AI very scary. Okay, I'm sorry, I'm getting all off topic. Okay,
No,
other
we only
questions?
have 2 extra minutes.
No, we're doing pretty well. So, which door? So, question: us classical mechanical people, not quantum mechanical. Which door did you come in today?
The open one.
Yes. We came in an open door. If we were electrons, what door would we come in? We would mostly come through that one, but we could also creep through the cracks in the bottom.
Whatever they fancy.
Yeah, electrons can behave strangely. So this is the quantum mechanical world. So you can be in many different places at once. There's something called the 2-slit experiment, which we'll talk about later. If you have 2 holes and electrons, if you have a single electron, so if you have a single electron and you shoot it towards these 2 holes, the electron can actually go through both holes at the same time. I mean, of course, it depends on how close they are. If they're like infinitely spaced apart, then no. But if they're close enough, the electron can actually, because it has uncertainty in its position, it can actually go through both holes at the same time. So that's one thing about electrons. When you start talking about quantum mechanics, the world just makes no sense. So like us and things like this water bottle and this textbook, these behave classically. So if I throw this water bottle towards a door, it's going to go through the door. If I have an electron, I throw it towards a door, it can split and go through both doors.
Get out.
And then come back somewhere else, yeah. So, and it can be in both places at once. So, but of course this only happens in really small scales. So that's some of the stuff we'll talk about. So this stuff I think is really cool. I mean, it's kind of weird, but I think it's cool. So, and I also remember when I was studying this in grad school, this is also when Harry Potter was very popular. So I was reading it. It made me a little comforted, actually. That like, oh, it's like magic. But okay. So let's talk about light and different types of radiation. So light is a transverse wave. So what is a transverse wave? Ocean wave is an example of transverse wave. An ocean wave goes this direction. Where does the water go? Up and down. It's perpendicular, so the wave direction is this way. The motion is this way. So the displacement is perpendicular to the motion of the wave. So light waves and other types of electromagnetic radiation are transverse waves. The wave goes this way. The electronic field, it goes this way. So like the electronic wave goes up, it goes down, up and down. So this is a light wave, and this electronic field. Then the magnetic field, similarly, is perpendicular to that. So the magnetic field goes this way. So it's an alternating, it's an oscillating, alternating electronic and magnetic field. So the super shortened Cliff Notes version of electricity and magnetism is electronic fields tend to attract and repel charges, and magnetic fields tend to turn them, make them twist. So that's the super abbreviated version of it. So if you wonder what a magnetic field and an electronic field does. So, but that's the wavelength that, I'm sorry, that's the type of radiation that happens with light and other types of electromagnetic radiation. And some other things. So here is a wavelength. So you can do a wavelength. You can measure it this way. You can do it crest to crest. You can do it trough to trough. But a wavelength is how long the wave is, very simply. And also frequency. Frequency is just how often you do something. Like, what is your eating frequency? Like me, I usually eat 3 meals, breakfast, lunch, and dinner, and usually kind of a snack around 4 o'clock-ish. Right, so I kind of eat 4 times a day-ish. But that's my frequency of eating, how many times I eat during the day. So here are some other light waves, and you have the wavelength and frequency. And for light and other radiation, if something has a high frequency, it has a low wavelength. So this is high frequency, high number per unit time. And this is a short wavelength. And this is a lower frequency with a higher wavelength. And in fact, red light does have a longer wavelength than violet light. Now, this beautiful picture here, this is my bad artist drawing of a boat. So here's a boat.
I did not see that.
Now you can't unsee it, right?
Don't quit your day job.
So I don't have a future in drawing boats on waveforms.
Triangle.
Is that what a boat is supposed to look like?
Yes.
You drew a triangle.
All those boats you've been looking at your whole life are done
Wrong.
yeah, they're totally wrong.
Now I know. Now I know.
You had to hear it here, yes. Okay.
Can't see it.
So let's say you're in your boat, your proper boat that is, and in the red storm, and then you're in your boat in a violet storm. So, and which one of these is going to rock your boat more? Which one is going to be a really powerful, heavy series of waves that are going to hit and rock your boat? Is it the red one or the violet one?
Violet one.
The violet,
Rocks
yes.
my boat.
Yes. The higher frequency, so when waves have higher frequency, they have more energy. And that's another thing we will talk about later on. What?
So like for me, for the frequent, are we talking about ocean waves here or like light waves? Or
Yes.
are they the same?
Well,
So
the
when you
property is the
measure
same.
the period, like when you check the surf and stuff and you measure the period, is that the same as the frequency of the rate?
I don't, that's the time between waves? Or is it a distance?
Let me try. You continue. I'm gonna do this separately.
If it's a time between waves, then that would be equal to frequency. Because the number per time is a frequency. The most common unit for frequency is hertz. It's just 1/seconds. Okay, but so some things. Speed is distance divided by time. So miles per hour, which means that I will move a distance of 55 miles over the time of 1 hour. My speed is 55 miles an hour. And when it comes to waves, this is the speed. And chemistry is weird. Physics, if you take physics class, wavelength is L and frequency is F. So for us in chemistry, our wavelength is lowercase lambda, and this is the lower letter nu, GNU, nu. So lambda nu, so lambda is wavelength, nu is frequency. This equals the speed. So what do I mean by that? So let's say that, what? Okay, so let's say, so you want speed, and I can kind of illustrate this also with my miming. Well, I guess I'm talking while I'm doing it as well. So here is my speed. So I can do a stride of 1 meter, and I can do one every second. So this is 1 meter a second. So 1 meter per second. So this is, I'm doing 1 every second, and my wavelength is 1 meter. Or, I'm trying not to twist my ankle again. So I can do like 20 centimeters as well. So I can go, right? So I've gone, it took me the same time. That's, I don't want to do it too much, I'll start running out of breath. But that was like, I did 5 oscillations, but also in 1 second, and I went 20 centimeters a second. So it's the same distance, right? But my speed's the same. So if I do 20 centimeters every 1/5 of a second, that's still 1 meter a second. Or I can do 1 meter stride, 1 every second, right? So that's just speed. That makes sense. If you have a wavelength, which is the length, and then you have your divided by time, 1 over time, that's your speed/velocity. And for electromagnetic radiation, the wavelength times the frequency equals c, or the speed of light. The speed of light is 3 times 10 to the 8 meters per second. So 300,000 kilometers a second, or about 186,000 miles a second. So it's
really fast.
Really fast relative to the Earth. Relative to astronomy, it's pretty slow. So for instance, the Earth is about 8 light minutes from the sun. It takes light 8 minutes to get from the surface of the sun to the Earth. So, and let's do a problem here. What is the wavelength if the frequency is 4.62 times 10 to the 14 inverse seconds or hertz? So the way you do this, so already written, wavelength, frequency is speed of light, which means our wavelength is the speed of light divided by the frequency, which is going to be speed of light 3 times 10 to the 8th meters per second divided by the frequency, 4.62 times 10 to the 14, 1 over seconds. And if you do this, you would get, I forgot. Go. Calculator.
Is it broken?
No? Oh shoot. I meant to hit delete and I hit all clear.
It's 6.49 times 10 to the -7.
Yep, 6.49 times 10 to the -7 meters, and then 6.49 times 10 to the -7 meters times 10 to the 9 nanometers per meter is 649 nanometers. So it's,
Does it matter which way that you do it because the book has it reversed? They have meters over 10 to the negative 9.
wait, it has what?
They have 6.49 times 10 to the negative 7th meters times 1 nanometer over 10 to the negative 9.
Oh yeah, that's fine.
It doesn't
But that's-
matter?
Yeah,
Either way?
yeah, because I wrote it this way because then the meters cancel.
Okay.
So, yeah, that's just this
A different
term
way of
flipped.
writing it,
Yeah. Because 1/1 billionth is inverse of 1 billion over 1. Okay. Other questions? I mean, all you're saying, I mean, with like, so the same argument is saying 100 centimeters is a meter, or a centimeter is a meter divided by 100. Okay.
What Greek letter is that for wavelength? Again, is that
Wavelength is
Rho?
lambda.
lambda?
Yeah. Lambda, here's capital lambda, here's lower lambda. And if you need to remember, have you seen Revenge of the Nerds?
Okay. No.
No, you haven't.
You watch
Oh.
a lot of TV.
That's the old stuff. It's trilambs. Okay.
Lambda.
Do you want to draw an entry?
I guess you don't have Greek, see, they don't have Greek
Lambda,
schools and
rho,
or Greek
and
whatever fraternity sororities here in Hawaii.
what are the three? Lambda, rho, and
Lambda Chi.
I don't know. I was Sigma Chi.
You were in? My ex was Phi Epsilon or something like that.
rho is credence.
Lambda, sigma, rho.
Okay.
Which one was sigma?
So anybody have any questions before moving
There's
on?
only one left.
Okay. So next thing we're talking about is the electromagnetic spectrum. And these are different types of radiation, and they do different things to matter. So I, myself, I'm a spectroscopist. So I look at how, I mean, I don't do research anymore, but I look at how matter and, well, energy, radiation, and matter interact with each other. Specifically, I look at infrared and visible. So I mean, there's different people who are good at different ranges of this. So let's start off with low energy, high wavelength, low energy. So radio waves. What do radio waves do? Radio waves, they change the magnetic properties of nuclei. So depends on the nucleus, and hitting a nucleus with radio waves is going to change the magnetic properties, magnetic moments typically of the nuclei. And what do we use radio waves for? We use them mostly for communication. So AM, radio, television, although TV is kind of going away, we're probably just going to stream stuff on the internet now. Well, we still broadcast TV, but I don't know how much longer we're going to do it. In a couple of decades, we probably won't. FM radio, and cell phones are actually microwaves. We'll get to microwaves next. Well, radio waves deal with nuclear moments, so magnetic properties of nuclei. And has anyone here ever had an MRI before? So if you've ever had an MRI, first of all, they're loud. And I didn't think I was claustrophobic until my nose was a half a centimeter away from the roof of that tube. Did you get stuck in the closed tube, or?
Yeah, it wasn't too bad.
Oh, really? Okay. I didn't like it. I just closed my eyes.
I wouldn't like that.
But they're loud. This is what it sounds like. It sounds like ka-chunk, ka-chunk, bah, bah, ka-chunk, ka-chunk, bah. So what they're doing, what's that?
Have you seen that video of they took the cover off of an MRI?
No.
And ran it?
No, I have not seen
It's
it.
pretty crazy.
Cool. Well, I don't want to look for it now. But what they're doing is that they're moving magnets. So the ka-chunk, ka-chunk, they're moving magnets around you. And then they're blasting you with radio waves. And what they do is the radio waves, they tune it to the frequency for hydrogen. And when you have the magnets, your hydrogen nuclei, they all align with the magnets. And then when the radio waves hit it, the radio waves can flip the the moment, what I mean, if it's spin up, you can flip it to spin down. And then they decay back down. As they decay, they emit radio waves. And then you detect the radio waves. And when you detect the radio waves, you can slice up the body into little sheets. And it tells you with those slices where a hydrogen atom is. And here is an MRI image of my lower back.
Whoa.
So if you notice,
Interesting.
this is my
Coccyx.
sacred, coccyx. And here is my L5, here's L4, L3, and you notice that these discs look different than these discs. So I had this taken several years ago, but I have what's called degenerative disc disease in my spine. And if you notice here, there's something called a protrusion because the edge of the disc ruptured and it was pushing into my spinal cord. And I can tell you, it is not a pleasant feeling. So, but this is just the hydrogen atom. So, it doesn't, I mean, of course, there's people that are much more trained than we are, but it's not that hard to see that this is different than this, than here, than that. So here you can image, these are bones, this is cartilage-ish, and this is spinal cord. So they get a bunch of images from this, and this is just one of them from my back. I have since recovered, at least. I mean, there's no reason to get another MRI image once I'm well, unless you're doing research on it, but insurance is not gonna pay for it, and I'm not gonna pay for it out of pocket just to satisfy my curiosity, right? So that's an MRI image, and MRIs are very, very safe. You can get all the MRIs you want. You can live in an MRI machine. It will not give you cancer. So, and then we get to microwaves. So radio waves deal with nuclear.
Radio waves are safe.
What's that?
Radio waves are safe.
Yes. Everything is safe up to ultraviolet. So then microwaves, what do microwaves do? Microwave, is it?
They use radiation.
Radiation, yeah. Everything's radiation. Microwaves makes molecules rotate. So if you have water molecules, and you put in a microwave oven, they rotate and they collide. It increases the temperature. So that's how microwave ovens work.
Their heat.
Yeah. Temperature.
Increases
Yeah.
their frequency.
So microwaves, they make molecules rotate. And we use microwaves for cell phone signals, and we also use it for radar. So radar uses microwaves. And the inventor of the microwave oven, he was working on a radar station, and he had a chocolate bar in his pocket. And as he was working on the radar and it was turned on, it melted the chocolate bar. So and from that, he was like, oh, we can use this to heat things up. I can make an oven out of this. And so, hence the microwave. So, and there's some controversy there. It hasn't been on the news that much anymore, but people were worried about people getting cancer from
Yeah.
cell phones.
That's my dad.
Your dad?
Yeah, he still says that to this day. Is he
Yeah.
right?
No.
I still use my headphones. Actually.
No. We'll talk about things later on with something called the photoelectric effect, but there's not enough energy in the microwaves to cause cancer. So what is cancer? Cancer is when a cell's DNA mutates in a specific fashion that it creates a cell that just keeps on dividing. So it's a very specific type of mutation that causes cancer. And in order to mutate something, you have to be able to break chemical bonds. You have to damage the cell's DNA specifically. And then the body has to repair it incorrectly. So what can cause a cell's DNA to damage? Radiation can. Specifically, ultraviolet, X-ray, and gamma rays. So past here, this is known as ionizing radiation. Chemicals can also do it. There are a lot of chemicals that are mutagens that can mutate DNA. Okay, so ionizing radiation. So what does a jumping bean do? It jumps. What does a kicking mule do? It kicks. What does ionizing radiation do?
Ionizes.
Ionizes. What does ionizing mean?
Bonding.
Not bonding.
Unbond.
It charges.
Charging.
Charges, right? An ion can be positive or negative. In this case, the ionizing radiation, it rips off electrons. So that's what an ionizing radiation does. It rips off electrons. You rip off electrons, you can break chemical bonds. So ultraviolet radiation, it causes surface ionization. So you can get skin cancer from the sun, but you can't get bone cancer. Well, if you get a malignant melanoma, it can spread to your bones, but sunlight directly cannot cause bone cancer. X-rays can cause skin cancer and bone cancer, and gamma rays can do whatever. They break it. Same thing as, well, they're stronger than X-rays. They can cause all sorts of bad things to happen. Okay, but let's go back to microwaves. So when you hear that about the cell phones,
Where did they even get the idea from then?
if you follow conspiracy theories, the conspiracy theory was that they were trying to get the Bluetooth people. There was a video that showed cell phones popping popcorn.
What?
Yeah, and supposedly it was a video that was made by Bluetooth devices, which I thought was funny because a Bluetooth device, what do you think a Bluetooth uses? It uses microwaves. So now you've got a radiation source by your gonads, another one by your brain. So you have two instead of one. So, whatever. But it doesn't matter because it doesn't cause cancer. I mean, so that's deductive reasoning with the chemical bonding stuff. You can do inductive reasoning where you assume it's true. Let's say microwaves did cause cancer. Who would get cancer?
Everybody.
Well, who would be especially vulnerable? So
Restaurant people.
Could be restaurant, yeah.
Gosh,
Even stronger than that, radar. Radar uses a bunch. So anyone who works around an airport, anyone who's been in the Navy vessels have radar towers on them. Very, very powerful microwaves.
I used to keep my phone in my bra, and my sister would get so mad, and she's like, "You're gonna get breast cancer."
My roommates finally got sick of me having our microwave unplugged for the past year, and I plugged it back in.
You're afraid of the microwaves?
I never had a microwave. My mom was the same way. She thought they caused cancer.
Yeah, my mom used to say that too.
So,
She goes, when you
like,
heat something in the microwave,
I
you
love
gotta stand to the
microwave.
side of it because the waves won't hit you. So I grew up.
Well, they can hit you. And
You're not supposed to stare at a
Right? Have
microwave,
you?
right?
You're not supposed to
like,
stand in
look
front of the
into
microwave.
it.
You stand to the side when you go.
it'll just heat you up. It'll make your water molecules rotate, and then you'll get hot.
And that's you stand in front of the microwave.
Yeah, no, I mean you can feel microwaves. They use those as
Especially if you're
non-violent.
Dispersal.
Yeah.
Huh?
Crowd dispersal.
What was that?
Microwave guns.
They make people feel really hot.
That's weird. So does surgery.
Okay.
Also makes you feel very hot.
Depends on the concentration. It's too sweet for me.
It's all we drink in China.
All right. Well, okay. So microwaves make molecules rotate. Then infrared light makes molecules vibrate. So if this is water, so this is above and beyond this class. But if this is oxygen, hydrogen, if you hit it, there's a couple different types of modes. This is known as an asymmetric stretch. This is a symmetric stretch, and this is a bending mode. So that's just for water though. So if you have something like my cotton shirt, if you hit it with infrared light, there's chains of sugar. So there's a 6-membered ring, and there's a bunch of chains of 6-membered rings. It'll make the stuff vibrate as it's going through. So that's what infrared light does. So when you put your hands over a fire, you feel the heat. The infrared light is coming, and it's making your body vibrate. So the molecules, at least, and the molecules on a molecular level are vibrating amongst each other. So that's infrared light. Then we get to visible light.
Stand in front of the microwave.
Was it?
Knowing all this, I probably still wouldn't stand in front of a microwave just because of how ingrained my mother would teach that.
Hey, whatever. But I I do a lot of outreach. I mean, and I had a kid ask me, he's like, is it bad for you to stick your face in front of the microwave? Will it really make you go blind and you have cancer? I said, no. She's like, ha, I knew it. Because I guess like he would like have a microwave and he would like, is it done yet? Is it done yet?
Yeah.
And so his parents were like, don't do that. That's dangerous.
Yeah, my mom always said you can't sit too close to the TV. It's bad for your eyes.
Yeah,
So that's
yeah.
That actually is true because of the cathode rays. There was radiation with that. The LCDs, no, you can stick your face in front of the LCD.
so funny.
You can do this all you want with an LCD screen. It's not gonna.
What about talking about chemical? Aren't preservatives really bad for you too? Don't those
Depends
cause
on the
cancer?
type. Depends on the type. I mean, like salt is a preservative, and I mean that's not gonna cause cancer because high
But it's
blood
like
pressure.
they're chemically altered.
Things like nitrites, those are mutagens.
Ooh.
So things like they use in salami and bologna, for instance.
Oh,
So that's yeah, the nitrites. So okay, but
ew. The
They're-
Starbucks pre-frozen breakfast sandwiches.
I don't know. I don't eat it. I guess I only eat at Starbucks when I'm traveling in the airports.
Smart, you'll probably never get cancer.
I don't know. I hope not. So it's better than wishing cancer.
I don't think anybody wishes for cancer.
Okay. So how are we doing for time?
It's
Okay.
4:01.
Oh, I got plenty of time. Okay, so visible light. So we moved on. Visible light. What does visible light do? Visible light makes electrons go up in energy. So I don't have a colored shirt on. Okay, let's say I had a green shirt on. If that means that the white light would come here, come to the molecules in my shirt. The white light is actually all colors for light. The white shirt, the green shirt would absorb the other wavelengths, but then it would either emit or the electrons would go up in energy and come down and emit the green light, and then you would observe the green light. So that's the way that colors work, among other things, and dyes. So visible light, this is also a light that visible is what we can see. So the book says visible light is between 700 and 400 nanometers. Although most humans can see down to about 800 nanometers. So to me, 800 nanometers looks like really dark brick red. It's like black with like kind of really heavy red. If you like the Crayola colors, it's like really brick color red. I can see to about 380 nanometers, and past 400 it's like a light lilac color into my eyes. So I don't know how common that is to see that far though. But some artists, so if you know Pierre-Auguste Renoir, he had cataracts and he had his cataracts removed, and his paintings changed, and people hypothesized that he was seen in the ultraviolet.
Huh.
So, but if you look at humans, so we have two different types of photosensitive cells in our eyes. We have rods and cones. So rods are light intensity only, and cones deal with colors. Most people have 3. Some people have 4. Some people have less than 3. If you have less than 3, that's also known as colorblind. And if you have more than 3, that's known as a tetrachrome. And this is the absorbance that we can tell. So like intensity versus wavelength, and we have red, green, and blue as humans. So we really see 3 colors, red, green, and blue. And of the colors we see the best, we see green the best. So what is the brightest color? What is the color that you look at and you're like, man, I cannot hear you. Your shirt is too loud in that color. What color is that?
Yellow.
Yellow. I think it's more the lime green color.
Yellow.
Yellow. You might be a tetrachrome. Tetrachromes hate yellow. So, but like the color they paint the fire trucks now, that fluorescent green color, that is a color.
What? I've never seen the lime green fire truck.
Oh, do they? Oh, I guess are they still red here? I guess I haven't seen
They're
this.
yellow.
They're yellow like
Yeah.
that. Look behind you, like that yellow.
Okay, yeah.
It's like a
I thought it
highlight
was
yellow.
green. Yeah,
Are
highlight.
you
Yeah.
colorblind?
No.
Yellow, it's not lime green.
Yeah.
My dad-
That's yellow.
My dad's colorblind. He thought bananas were purple for the longest time.
A lot of the guys in my family are colorblind.
Is your son? Or do you have any?
I don't know if he's colorblind yet.
Okay. Because it's carried on the.
My granny would carry the gene and she would give them to all the boys.
Yeah. No, I'm definitely not colorblind. I might actually be a tetrachrome. I'm
My
not
nephew
sure.
mixes brown and orange. He'll never be an electrician.
But well, on an unrelated note, I thought this was interesting. People that are born deaf and they can hear later on, they expect the sun to have a sound. And they're surprised. They're surprised that the sun doesn't have a sound.
Interesting.
But that's hearing, of course, back to vision. In my personal opinion, I think of all the species, I think humans see the best. So, although we have 3 types of color-sensitive cells, there's other species. Mantis shrimp have 11, and eagles, they can see better than this, like the raptors and birds of prey. They, like eagles, they can see really finely, but they have tiny brains. Whereas we may not see as much detail as an eagle, but we have a brain that can interpret it. And we can only see 3 colors, but mantis shrimp can see 11, but they have tiny brains too. They can't appreciate what those colors mean. So,
are there animals that can have like a zoom effect with their eyes?
not that I
The
am
zoom
aware of.
effect with their eyes.
Yeah, not that I'm aware of. So, we don't have a zoom, but we focus our eyes near and far. So I guess you could argue that's more of it's
Like a
I'm
focal
zooming
thing.
right now.
it's more of a focus. I don't know. That's really a zoom. I'm not looking at a chemistry book. I'm like, oh, I see it closer. You know, the zoom is like this.
Yeah.
So,
Or maybe not telescopic.
oh, of course, our eyes
Yeah.
work that way if you have 2 of them.
Yeah.
Right. I mean, that's how depth perception works.
Yeah.
So, okay, but since we only have 3 different colors that we see, our brains interpret the relative signal. So like this signal here would be like yellow or orange. And our brain just interprets the relative signal like, oh, there's no blue and there's so much red and there's so much green. I interpret that as yellow or orange or something like that. And another problem with humans is that we really can't tell the difference between violet and purple.
I
So-
can.
I'm impressed. So violet is light at 400 nanometers. So what's purple?
Light at 750.
And how do you make purple in our class?
It's red and blue.
Red and blue, yeah. Because our red sensor absorbs in the blue as well. So if you give a human red and blue, we can't tell the difference between red and blue and violet. It gives us the same signal to our brain. So that's like an interesting thing about good old-fashioned humans. But yeah, we see green the best. It's also the yellow-green color. I mean like this color. I think that looks brighter than yellow, but
No.
all right.
And something that's interesting to learn in art class too is that color is relative. It's like what it's next to, you can.
Yeah, that's
change
perception. Yeah,
Yeah.
that's a whole other.
But so like you can trick your eyes
Yeah.
to see different colors based on what's around you.
He went to a fancy art school.
Well, it's also in psychology. I learned that in psychology, not art school. It's all perception stuff. Okay, so that's visible light, and it's one that we use, at least our eyes use. But most people can see down into the infrared. But look what the words mean. Infrared, less than red. Infra means less. And ultraviolet, beyond violet. So let's go then beyond violet. So ultraviolet. Ultraviolet is now ionizing radiation. And ionizing radiation is dangerous. And ultraviolet radiation, the sunlight has ultraviolet radiation. And we do have colors, of course we can't see, but there are colors of ultraviolet radiation. We group them into what's known as UVA, UVB, UVC, and then beyond that we call it vacuum ultraviolet. So vacuum ultraviolet's kind of halfway through. The atmosphere absorbs that. So it doesn't quite to X-rays. But UVA, UVB, and UVC are not absorbed by the atmosphere. UVA is the primary cause of wrinkles. So what a wrinkle is it's scarring of your dermal layers, your skin, and then your epidermis, the top layer, folds over it. So there's a couple ways you can have wrinkles. You can be born with it. I have a wrinkle here that I was born with. You can do it by repetitive motion. So like if you've seen an old person, you can kind of see, oh, it's a happy person because you get the smiles, and then that's a sad person. It's like the frowny face wrinkles.
Parentheses.
Yeah.
Yeah.
Yes. So you can kind of tell. That's one way to get wrinkles.
Feet is stress.
Could be. Yeah. Then but the primary cause of wrinkles is sunlight, and specifically UVA, and UVB. UVB radiation is what causes sunburn, suntans. We also use it to make vitamin D. So we humans, we are slightly photosynthetic, so we can make provitamin D3 from cholesterol and sunlight and UVB radiation. UVB also causes cancer, carcinomas, melanomas. So sunscreen blocks UVB. If you get a broad spectrum sunscreen, it can block UVA as well. So if your sunscreen says anti-aging or broad spectrum, it'll block UVA. But it only blocks about half. So UVB though, like SPF 30, that means 1/30th of it gets through. So SPF 50 is 1/50th. And it's only going to block about half of the UVA.
So the lower the number, the better it is at blocking.
The higher the number. So 1/30, that's about 3%.
1/30th?
Yeah,
Oh,
and 1/50th is about 2%.
I thought the number had to do with the duration of time it blocks.
No, it's how much radiation absorbs. How much UVB absorbs.
There was that video of like the infrared camera, and then people are putting sunscreen on, and then it like turns black where they put sunscreen on.
Well, it would be ultraviolet, it wouldn't be infrared. Yep, that. And you can see freckles on people too. There's like all sorts of stuff. So, but ultraviolet, what does ultraviolet do? It makes big jumps in electron energy level, and ultraviolet light can rip off electrons on the top, on the surface of atoms and molecules. So they go for the valence or outer shell. X-rays are higher energy. X-rays can rip off the top layer, and they can also rip off the core, the bottom layers of electrons. So X-rays can cause skin cancer, but they can also cause bone cancer. So so skin cancer with X-rays, apparently dentists before, like I just went to the dentist last week. I hate going to the dentist. But I mean, because they scrape my teeth. It's not a very pleasant process. But they took X-rays, and they told me to hold the thing and bite down, and they took the X-ray. Back in the olden days, the dentist would put his or her fingers in your mouth, and here you go, and put it in there. So their fingers got all manky. And besides that, people don't go to the dentist, and now they have really radiation damaged hands. Made them less popular. At least nowadays, people leave the room, right? So, but X-rays also cause that. So, but X-rays are dangerous. But I always think it's funny X-rays go in straight lines, and then when they take the X-ray in my mouth, they have me put on a lead vest. I'm like, why the heck are you doing that? Because it's like a flashlight. It's going to shine, as a cone in the direction there. It's not gonna hit my chest or my lap, right? But around the neck, that's a good idea because it'll protect your thyroid. So the neck's good, but everything else is kind of stupid. But
sense of security.
Yeah.
A false sense of security.
Yeah, if you put a lead vest on me, sure. So, okay.
What is in that the little thing they put in your mouth? That's the film.
Yeah. I don't know what exactly film they use for now. They probably use cesium iodide or something like that. Usually some sort of alkali halide is typically used because that's how they can detect radiation that way. And then it flashes and can get a signal from that. And gamma rays, so electrons have energy levels, so do protons and neutrons in the nucleus. And those gamma rays affect the energy levels of the nucleus. And they're also very high energy. Whenever a gamma ray hits an electron, it just ejects it. It shoots it right out. So gamma rays are very harmful.
That's how you get the whole.
The Hulk, well, radiation, all it does, it breaks chemical bonds on an atomic and molecular, well, it could be molecular level. So, I mean, radiation just causes damage. I mean, it's like, radiation sickness is like having the flu. I mean, I've never had it, but, I mean, it just beats you down. Okay, so my shut up alarm's about to go off. So, okay, and actually ended at the same time, well, the same place as the previous class. So, I thought I was going to have to break out some questions for you, but I guess not.
We lost our 6 minutes.
Yes, but you gained so much more knowledge. It's 6 minutes of interest. Does anybody have any questions, I guess? Okay. All right. See you guys Wednesday.
Yeah, thank you.